Let's get started then. Thank you, Ken and Kevin, for the introduction. And let's get started with the first technical session. So I will be talking about a solution we developed called Ghelamco Alert. And the main goal of that solution was to toy a bit with IoT devices, Raspberry Pi, and to make our life in the IoT world a bit easier by leveraging some additional cloud capabilities from AWS in this case. So first things first, who am I? My name is Bas Moorkens. I am an AWS architect at Ordina. I mainly build and design systems on AWS, most of all to run Java and JavaScript applications. And I also do DevOpsy things with customers. That mostly boils down to keeping the lights on in production a lot of the time. If you'd like to contact me, you can find me on Telegram or Twitter, or even better, you can invite me for a beer. I'm always down to have a beer. Let's get started on. First of all, some of you probably know this, some of you might not know this. At Ordina, we have an office in the Ghelamco Arena in Ghent, which is obviously pretty nice because we have a rather unique view from that office. But the drawback of having the office at the Ghelamco Arena is that we also share the parking lot with the football club. So on the days that there is a football match going on at Ghent, we need to make sure that we leave our parking spaces at least 3 hours before the game. Otherwise, we could be penalized with fees up to 500 euros per car that is still left. So in the past, we noticed that sometimes people did actually forget this, and we got hit with some fines. And of course, we'd rather spend that money on other things like team buildings, pizzas, and beer. So we thought to ourselves, hey, is there something we can do to make this easier? So the first thing that popped up was, hey, we can check the website manually and we can actually ask people to leave early. But that seems pretty low tech, right? I mean, we are software engineers, right? So let's build a simple automated application to do this for us. We then got started on designing an application, and the final result looked a bit like this. So the word simple is probably an exaggeration here because I couldn't even fit the entire architecture on one slide anymore. But I don't want you guys to worry because we'll be talking about a lot of the different components separately. And I'm gonna start with a very basic setup and walk you through it, how we built it up step by step. So let's get cracking on that. To start it off, very simple. What is actually the goal that we want to achieve here? Well, in essence, it's pretty simple, right? We just want to notify people in the office in Ghent in a visual way that they have to leave the. So the best way that we could think of was, hey, let's use an alert light, like the one you're seeing down there. Now, having an alert light is pretty fun, but in itself, it's not that great because somebody has to turn on the light and you don't want anybody standing around all day to push a button. So we thought to ourselves, hey, how can we control this light? So that's where the Raspberry Pi came into picture. So we thought to ourselves, hey, this could be a great component to control the light for us. And for you guys that don't know the Raspberry Pi, it kind of looks like this. So Raspberry Pi is one integrated chip, which has a CPU, processor, RAM, everything attached to it. And it's very small and pretty cheap, especially if you compare it to regular servers or laptops or desktop computers. So it was pretty ideal for our use case. The only thing that is a bit different from regular computing hardware is that the Raspberry Pi uses an ARM architecture like your cell phone. So it will not run any software that is built for x64 or x86 architectures. So this gets important later on in the presentation. Now that we have our piece of computing software, hardware, we can hook it up to a relay board. So you'll see later on in the demo that we will connect this Raspberry Pi to a relay board that's now pictured on the right side. And then that will be attached to an alert light, and that will be our final hardware setup. So, of course, now we have an hardware setup, which is great, but we still don't want to control things manually, but instead we want to do it automatically. So, hey, let's build some software to do it for us. And we are still called JWorks, so let's build a Java application with our most popular framework, Spring Boot. And we will also be using a bit of a special database here. It's called the H2 database, which is an in-memory database. But I'll circle back to that on in about 2 or 3 slides. So for the features of this software, what do we actually want this program to do? So the first feature is we want to automatically get all the games from the website, right? So we built a piece of software that scrapes the website of K-Agent, and it checks the website every 4 hours. You can see that on the right side of the screen. It looks like that. And every 4 hours, our software will check, are there any new games added? Are there games rescheduled? Or are there games canceled? Once it finds a new game or a rescheduled game, it will generate 3 default alerts for each new game or that rescheduled game. The first alert will be at noon that day. The second alert will be T-minus 5 hours. And the last alert will be T-minus 3.5 hours. This is to ensure that everybody has had enough visual notifications by the time we actually have to leave. So in the last step of this process, all that data that we've parsed and created, we will save that in our H2 database. So we have access to that all the time, and we don't need to scrape the website every minute. Now, the next set of features is probably pretty straightforward. We want to actually control the alert light. So it's pretty easy based on what we said in the previous slide. So we want to turn on the light whenever we reach the start time of an alert. And we of course want to turn off the light again when the end time of that alert is reached. So that brings us to following architectural picture. Voila. This is version 1 of the architecture, and it's actually not that complex. So the big green box is the Raspberry Pi in our case. And you can see that it's hardwired to the IoT alert light. So that is a physical connection. And on that Raspberry Pi device, we will run our Spring Boot application. And that Spring Boot application will start our H2 database server, which is embedded into it. Now, a small note on this H2 database. Normally, it's used a lot for testing stuff, and it's totally in memory. But you can also run it backed by a file on a file system. So that's what we actually did. So the H2 database saves its changes and state to a file on the Raspberry Pi's SD card, so that whenever our application restarts or gets redeployed, we don't lose all our data. We would have to regenerate all the games and alerts every time otherwise. So that would be pretty dumb, right? Now, we still had some open questions when we reached this point, because that's a pretty basic setup. The first question we had was like, can we run this Raspberry Pi on the Ordina network? So we went to corporate IT, and they of course said, hell no, you cannot do that because it's not compliant with our IT policy. So this has a couple of implications for us, because there are 2 basic ways to interface with your Raspberry Pi. So the first is you hook up an HDMI cable to it and just have physical access on the screen. And the second way is you use SSH to SSH into your box and control it that way from the terminal. But since we cannot run it on the Ordina network, so instead we will have to use a public network, the guest Wi-Fi or a SIM card. It will be pretty difficult for us to access the device over SSH. And I sure as hell don't want to drive to Ghent every time I have to change something on the project. So that left us in a bit of a pickle. So the questions that now arose were, how can we run the application on the Raspberry Pi without having that access? For example, how can we make sure that the application has started, that the application is still running, that it hasn't crashed? The second question was, can we monitor the state of that application and the Raspberry Pi without having that access? Can we somehow communicate with our application to make it do additional things? Because right now we have a pretty basic application. So you have the automatic alerts and the light goes on and off, but that's pretty basic. So we might want to add extra features where a user can, for example, snooze an alert or create a custom event. And last but not least, the most interesting part, can we somehow update this application and the software that's running on top of it without having the access to the device itself? So this is where AWS comes into play, because without using AWS or another cloud platform, it would be pretty difficult. But we found a way by using AWS, and I will be focusing on three major services here. So the first one is AWS IoT, which allows us to securely connect our IoT devices to the AWS cloud. So what this means in practice is that you get security because on AWS IoT, you generate some certificates and you then upload those certificates on your device. So to the Raspberry Pi in our case. Those certificates are then used to set up a line of communication between the device and AWS. This communication runs on top of the MQTT protocol. Now, for those of you who are not aware what this protocol is, it's basically a very secured and lightweight pub/sub protocol. So that means that on one side, for example, the AWS IoT side, you push a message on an MQTT topic. And on the other side, in our case, the Raspberry Pi, you will have a subscriber to that topic, which will pull the messages back off it. So that's an easy way to set up some sort of communication between AWS and your device. So this way we can send jobs from AWS IoT to the Raspberry Pi, and we can add custom code in our application to execute some code based upon the job we receive. There will be some examples of this in the demo later on as well. So the second service I want to introduce is AWS Green Grass. AWS Green Grass is actually an extension on top of AWS IoT. And their slogan is Green Grass brings the AWS cloud to your IoT device. Now, this sounds pretty fancy, but it's actually not that difficult to set up. So in Green Grass, you create a Green Grass group, and that group will contain all your IoT devices. In our case, it's just one, the Raspberry Pi. And each Green Grass group also has a Green Grass core. So the Green Grass core is an interesting concept because this core device will typically have a nice amount of CPU and RAM. So like, for example, the Raspberry Pi. And onto that core device, you can then run additional AWS capabilities like Lambda functions or Docker containers. So in our case, in our use case, we went for the Docker containers because it just made more sense. And we are running these containers by using Docker Compose. And finally, Green Grass also allows you to do over-the-air updates of the software itself. So this is important later on as well. Now, the last service I quickly want to mention is AWS Cloud Watch, which is a monitoring and observability service. And most people that are familiar with the cloud have already heard of this. But what a lot of people don't know is you can also use Cloud Watch to monitor devices from your on-premise environment. So in our case, it can as well monitor the Raspberry Pi. So what can we do with it? We can push log files from the Raspberry into CloudWatch. We can push metrics from our device into CloudWatch. We can then build dashboards and graphs from that metric data, as I will demonstrate in a minute. And we can build alarms that notify us when things are going wrong. So I have a quick demonstration of this. So here we are in the CloudWatch screen of AWS. And when I go to log groups and I search for the name of our application, Gela Business, then you can see that these are basically just the application logs from the Spring Boot application. So they are streamed in near real time to CloudWatch. So this is actually pretty nice for us because we don't need to have physical access or SSH access anymore to be able to know what's going on in our device. Now, the second part that I wanted to show here is the dashboards that we built. So we created a nice dashboard for this application, and it's separated into two lanes. So the top side is technical stuff, and the bottom side is more business-related metrics. In the top side here, you can see this graph, the RPI backend status, which basically is just a heartbeat process. So every 5 minutes, our application on the Raspberry Pi sends a heartbeat value into AWS Cloud Watch, just as the value 1. And whenever that value does not get sent anymore, we're in trouble because we probably lost internet connection or the device has no power anymore and it's down. So on the right side, you can see we created an alarm based on that. So if I click that open, you can see that the alarm is based on the RPI backend status metric that I just showed you. And whenever we do not receive data points for 10 minutes, or the value that we receive is less than 1, the alarm will go off. Now, what this does is when the alarm goes off, I get notified by email, which is not that cool actually. But anyways, at the bottom side here, we have more business-related metrics. So if you remember back to when I talked about the application itself, whenever we add events or cancel events or update events, we probably want to be aware of that. And the same applies for whenever we start alerts or snooze them or stop them. So our application is actually pushing these values into CloudWatch as well. So whenever we scrape the website and we add another event, like for example here, that metric gets pushed into CloudWatch, so it appears in this dashboard. This is also very useful because we can see in our dashboard here pretty easy what's going on in the application, and we don't need any physical access or SSH access into that box. Right, so let's now see how these three services can help us solve the problems we talked about earlier. So the first question was, how should we run our application? Well, we can set up our Raspberry Pi as a Green Grass core device, which we did. We then installed the Green Grass daemon and its dependencies on that Raspberry Pi. And this was actually pretty interesting because here the chipset architecture comes into play again. On a normal computer or server, you have no problem installing Docker and Docker Compose, which are the dependencies for Green Grass. But on the Raspberry Pi, it was a bit more difficult because there is no version of Docker Compose that is compiled for the ARM chipset. So we actually had to compile this from scratch for ARM. Just an interesting side note. Once you have everything installed, you just have to create a Docker image for your application. Then we create a Docker Compose file to configure how our application should run. So for example, which ports should be open, which volume should be mapped, stuff like that. And then at the end, we just create a Green Grass deployment, and that's basically everything. Once all these steps are done, you can just run the Docker container on the Raspberry Pi and everything should be taken care of. For the second question, can we monitor the state of the Raspberry Pi without having access to that device? Well, yeah, as I already showed you, we can pretty easily do that through Cloud Watch. So we send our logs and the Green Grass logs into AWS Cloud Watch. We push our metrics from the Raspberry Pi from our application into Cloud Watch, and we then use those metrics to build that monitoring dashboard that I showed you. And we also created that nice alert. The third question was, can we interface with our application so we can make it do additional things? The answer is, hell yeah, we can. So this will be demoed in the demo later on as well, but we can pretty easily send jobs over the MQTT protocol to our application. This is all supported by the AWS IoT service. So how that actually works is, well, AWS IoT creates the job document and puts it on an MQTT topic. Our application, which is running on the Raspberry Pi, then listens to that topic and has custom code to execute whatever command we're sending. And once the application has processed that command correctly, it puts a response back on the topic to AWS IoT so that AWS IoT knows, hey, the job was handled successfully, or if things failed, you can put a message, hey, there was a problem executing this. But this will be demoed later on in the movie I recorded. And then the last question we still had is, how can we update the application and other software on our device without having access to the device itself? Well, we are using Greengrass to do that again. So using Greengrass, you can pretty easily deploy Docker containers to the Greengrass core. And the Greengrass also can apply those over-the-air updates of the Greengrass daemon itself. The only thing that's really missing in the setup is, say you have a vulnerability in the OS, or you need to patch the OS. That is not supported out of the box, but you could work around this if you really wanted, by, say, creating a job in the application, which listens to an AWS IoT topic. Say it listens for a command patch OS, and then in your code, you could actually do the OS patching that you wanted. For example, yum upgrade, yum update, stuff like that. But if we now combine all these previous answers into one statement, I can say that we can now pretty much build a normal CICD pipeline. So we can build and deploy our software from our GitHub repository straight onto the Raspberry Pi device. Let's have a look how that looks. So here is a simplified diagram of that. So as you can see in the top left corner, we are using Azure DevOps as our CI/CD tooling system. And the first step is pretty easy, as you would expect. We build and test our Java code. Then in the second step, we package our Java artifact into a Docker image, and we add other dependencies that are needed. For example, certificates for the Raspberry Pi, other config files, stuff like that. Once the image is fully built, we can then push that image into ECR, which is the Elastic Container Repository from AWS. So this is just a managed registry, nothing too fancy. But the important thing to note about this step is, once you push the image, you get a tag returned from ECR, and we will be using that version tag to fill in our Docker Compose YAML file in the fourth step. So once we fill in the correct version that we need, we will upload that Docker Compose file onto S3, which is just a file system in the cloud. And then the final step of our CI/CD pipeline in Azure will just be, we create a new Greengrass deployment. Once that deployment is created, the Greengrass service sends it onto the Greengrass daemon that's running on the Raspberry Pi. So now we are at the bottom left of the diagram. So we just received the new deployment on the Raspberry Pi. The Greengrass daemon on the Pi will then download that Docker Compose file we created. It will open that file and check for the ECR image that it should pull. So that's where the tag comes in play again. Finally, it will download that image. It will terminate the container that's currently running, and it will start our new container. So all in all, by using AWS Green Grass, our CICD process looks not that different from a normal CICD pipeline, like for example, you would deploy to Kubernetes or virtual machines. Only the Green Grass part is really specific for our IoT setup here. Now that everything about that is said and done, let's look at version 2 of our project. Voila. So we didn't actually introduce that much complexity here. You can see in the middle, we still have our Raspberry Pi. The only thing we did is we installed the Green Grass agent, which is running a Docker and Docker Compose. But on the Raspberry Pi, everything has stayed pretty much the same for the rest. We did, however, introduce 2 additional AWS services, so Cloud Watch and AWS IoT, so that we can monitor our application and Raspberry Pi, and we can send it custom commands. Now, I can already hear you guys think, this is nice, huh? But our users' only interaction with our system is seeing the alert light turn on and off, which seems pretty rudimentary, right? So let's try and build a small web application so that our users can interact with our project. The only question that we really had was, how can we access the data from our Raspberry Pi from our web application? Because the data in the Raspberry Pi is stored in the H2 database and it won't be easily accessible from somewhere else. And our web application will live in the cloud. So how do we bridge that gap? So we came up with a pretty simple solution for that. So this is the final diagram of the architecture. And as you can see, I introduced the web application at the top left side. So that's just an Angular web application. Of course, the actual implementation is a lot more complex, like in the first diagram I showed, but I don't have enough time to cover all that stuff anymore. So let's just keep it on. We have the Angular web application at the top left. And we introduced as well the DynamoDB on the right side of this diagram. So what we are doing there is actually pretty simple. So whenever our backend on the Raspberry Pi changes something in the database, so in the H2 database, it will also replicate that change to the DynamoDB table, which lives in the cloud. So the result is that we actually have a duplicate of our database in DynamoDB, which our application, our web application in the cloud can then use. And the second part to complete this is our web application can also use AWS IoT to send custom commands to our Spring Boot backend on the Raspberry Pi device. Okay. Now I have a demo movie ready. It's supposed to play with sound. So can you guys give me a quick heads up if there's no sound playing when I start it?
Sound.
Is there a problem with the sound?
So, welcome to the demo of.
It should be hearable, audible right now, right?
Welcome to the demo of the Ghelamco alert project. So on the left side of my screen, you can see a live video feed of the setup that I physically have. So we have the Raspberry Pi device, we have the relay controller, and at the top we have the light that functions as an alert light in our test setup. On the right side of the screen, we have the web application open that we built. So let's take a quick look into that application. As you can see, when the application opens, we get a list of the upcoming events and we get a list of all the past events. Now, the next upcoming event is still a couple of weeks away, so I don't want to wait that long to turn on an alert light. So let's create a custom event. So to create a custom event, we have to fill in a title. We have to provide it a date, or today's date, and then we give it a suitable time. So let's take 8 p.m. Voila. Now that I created this event, you can see that what we actually created is an AWS IoT job. So our front end took the values that we filled in, created an AWS IoT object out of it, and sent that job object to the Raspberry Pi. So once this is processed, voila, we should be able to see the new event on our dashboard. Voila, there it is. So we get this new event, which has 3 standard alerts, right? So the first 2 alerts have already passed because they were right before noon and right after noon. So let's manipulate the last alert that is still to come. Let's put it in 1 minute from now. Okay. So in about a minute, the alert should be going off on the Raspberry Pi. And again, the way we did this is by sending an AWS IoT job request to the Raspberry Pi. And voila. As you can see, the job is processed. The alert light has turned on. And when we now open the custom event again, you can see that the state of our alert light is active. Great. So to end the demo, I'm going to turn off the light again by snoozing the alert. So I click the snooze alert button. And once again, when we look at the job overview page, we can see that another job was created that goes to AWS IoT. By the way, we could also check it in this view. So this is the AWS console of AWS IoT. Now, if we look at the jobs for this device, you can see that one job is queued. And when we look at the details of that job, you can see that we want to snooze the alert with ID 281. And as you noticed, the alert light has effectively turned off again. So the job is processed. And when we now look at our custom event, you can see that the alert is active, but it has been snoozed. So,
right. So I hope that was a bit understandable, the demo. Originally, there was a lot more talk about this because the entire part in the cloud is pretty complex as well, but I didn't have enough time to explain everything. So if you are still interested or want to know more, you can find the blog post about this project, which has a lot more detail about everything. You can find it on the link that is on the screen right now. So the Ordina JWorks tech blog. And that's about it for me. So if there are any questions, I think we still have a couple of minutes to do that.
Hello, Bas. Yes, I was going through the questions. There was one question for you.
Yeah.
get it at a moment's notice here.
Is it somewhere in the chat or?
Yes. The question was from Johan Silgens. Could this project also be done by using a microcontroller, say like an Arduino or an ASP-enabled platform?
Yeah, you could probably do it as well. I'm not that familiar with those devices actually, but I mean, in essence, it's pretty simple, right? You need some kind of hardware that can control an alert light. So I assume the Ordina can do that as well. But what the actual added benefit here is the green grass setup, right? So we get all this extra capabilities from AWS to deploy stuff on it. If you're okay with not having that, then you can do it with a bit more basic. But I found it very pleasant to work with it like this, because I'm really not the kind of guy to go physically to a device and install stuff on it. That's just too much 90s for me. But I'm pretty sure you can do the essence as well with another device, yeah.
Yeah, maybe I can expand on that. Well, the big problem with Arduino is the limited processor capacity and limited storage. So it's not a really great platform to run Docker containers on. You won't be able to do that. It's too constrained device regarding CPU and storage. So yeah, I don't think that would really work that well. But we are working, the VUB is looking at something called WebAssembly to have something similar like that, but for really low power, very constrained devices. The printer has to be so much smaller than like Raspberry Pi, which is basically just a full-blown computer. So microcontrollers are something different.
Yeah, what you could do is you could have a microcontroller to operate the light, and then you could put that in a green grass group, but you would need to have another device which acts as your core, as your green grass core, and that device should have an adequate number of CPU and memory. Actually, we do the same at a customer, so they have a lot of IoT sensors in their warehouse, and those IoT sensors are in a green grass group. But the green grass core is just a virtual machine in their on-premise data center, because it needs to have all that added compute capabilities. So you can't really do that with a very simple device. So were there other questions, Kevin? No? Okay. Yeah, thank you for your time then. I'll be signing off then, I guess.
Thank you for the presentation.
Thank you.
I'll mute myself again.
Okay, thank you, Bas, for the epic presentation. We will now have a few minutes to grab something to eat, or go to the toilet, or switch tracks if you need to or want to. And we will continue at 2:10 with the infrastructure is code with the AWS Cloud Development Kit by Kevin Azar.